Hi guys, welcome to my learning mechanics series for beginners number 2. We will continue where we left off in the first video where we learned about what scalars and vectors are. And in this video we will learn how to write vectors, how to draw vectors, and how to add vectors together. So let's get started. So when writing a scalar, we use symbols to represent measurements. For example, v represents speed. To write this as velocity, its vector component, we put a small arrow on top of the v. So v with a small arrow on top of it represents velocity. So speed is scalar and velocity is a vector. You can also write speed as the magnitude. So the two vertical lines here we see, they represent absolute value or just the size of the velocity vector. And from the previous video we found out that speed is just the size of the velocity vector. So when we have a vector, the size of the vector is its scalar component. So speed is just the size of the velocity vector, and that's what those two vertical lines represent. So having v like this or having like this, they are identical. There's no difference between them. So let's have a look at some scalars and vectors. So let me just put the same scalars and vectors we had from the previous video down. And to write distance, we use either d, s, or r, but usually it's r. For speed we use v, for mass we use m, for energy we use e, u, or w, for time we use t, for displacement it's vector, the distance's vector component is r with an arrow on top of it, and velocity is just speed, which is v with an arrow on top of it. Acceleration is a with an arrow on top of it. Force is f, a capital F with an arrow on top of it, and momentum is p with an arrow on top of it. Alright, so now let's have a look at how to draw vectors. So to draw vectors you use arrows. Now this is important. The length of the arrow is the size of the vector. The direction of the arrow is the direction of the vector. So let's look at an example. So we are going to be working in 2D space. So let's define our axes. We have a y-axis, which is vertically up, and x-axis, which is to the right. These are just completely standard. So let's say we have a ball, and we roll the ball in this direction here. So R1 is the vector. It follows the orange arrow. We are rolling the ball along this arrow. So let's just put some dimensions in. So we are rolling the ball towards a wall, and the ball rolls 5 meters to the right and 5 meters up. So let's write down this vector. We need to give it the vector size, and we also need to give the direction it's pointing. So the direction would be the x degrees here. This is the angle the vector makes with the x-axis. So the first method we're going to use is a geometric approach. So the length of the vector, which is the magnitude of R1, we can use Pythagoras here. It's a right angle triangle. It's just the square root of 5 squared plus 5 squared. And if you work that out, it's 7.07 meters. So now we can also work out what x degrees is, the angle the vector makes with the x-axis. And again, this is just trigonometry, and you can work it out quite simply because it's a right angle triangle. And it comes out to be 45 degrees. So now how do we write this down? Well, we write it down as follows. We have R1 with an arrow on top of the R1, because it's a vector, is 7.07 meters at an angle of 45 degrees with respect to the x-axis, and is traveling to the right. So the first thing is the 7.07 meters. So that's the length of the vector. And now and after you give the length, you give the direction the vector is pointing. So we have an angle of 45 degrees with respect to the x-axis, and is traveling to the right. Nice and easy. This is what we call polar form. Alright. So now let's look at adding two vectors together. So we have the same scenario. We have the same ball, we're rolling it towards the wall, and it's exactly the same. Now we say that the ball rebounds off the wall like this. It rebounds at the same angle, it hits the wall, and this time it only travels 3 meters to the left and 3 meters up. So it doesn't travel the same amount. It doesn't travel 5 meters. It travels 3 meters now, and the ball ends up over there. And using trig, you can find out that the two vectors have a right angle between them. And what we want to write down is the resultant vector. So we are going to add the vectors r1 and r2 together, and if you do that, you get the resultant vector r. And the resultant vector represents where we started, which is over here, and where we ended. It's simply an arrow from where we started and ends at where we ended. And the reason why this is useful is because this just gives a direct route from where we started and where we ended, and doesn't really care about the route we took. It doesn't give us any information about the route we took. It's just where we started, where we entered, and where we ended. It's the shortest possible route, and it is the most direct route. It's the resultant vector. So to write our arrow on top of it, we first have r1 from the previous slide is 7.07 meters at an angle of 45 degrees, and is traveling to the right. We can also find r2. Again, the size of r2 would be square root of 3 squared plus 3 squared, which comes out as 4.24 meters, and r2 makes an angle 45 degrees with respect to the x-axis, and this time it is going to the left. So to add vectors, you attach the tail of one vector to the head of the other one, just how we see in this diagram. The tail, which is the back of the vector of r2, is attached to the head of r1. So think of these as arrows. You have the head of the arrow and the tail of the arrow. So the tail of r2 is attached to the head of r1, exactly like in this diagram. And now we use a vector notation. So we're adding the two vectors together. So that's exactly what this equation shows. We have the resultant vector r, and what we're doing is we're just adding r1 and r2 together, and since they are vectors, we have to put an arrow on top of each letter. And now something very important to note. The magnitude of the resultant vector does not necessarily equal the magnitude of r1 and added to the magnitude of r2. So the reason for this is because r1 and r2 are not pointing in the same direction. r1 is going to the right and r2 is going to the left. So quite obviously the length of r is not the length of r1 plus the length of r2. It's just not true. The only scenario where this would be true is if r1 and r2 are traveling in exactly the same direction. But in this case, that is not the case. So using trigonometry, we know what length of r1 is, and we know what the length of r2 is, so we can quite easily work out the length of r. So it's the square root of the length of r1 squared plus the length of r2 squared, which is 8.25 meters. And using more trig, we can work out the angle the resultant vector r makes with the x-axis. So that's x degrees. We can work that out to be 76 degrees, and you can use trigonometry to work this out again. How I did it was I found this angle here by taking the inverse tan of r2 divided by r1 and then added that to 45 degrees. It's just trigonometry. So therefore, r, the resultant vector, is 8.25 meters at an angle of 76 degrees to the x-axis, and is traveling to the right. Right? Now for this example, it's quite easy to add the two vectors together using this geometric approach. But let's say the angle between R1 and R2 is not a right angle, and if that's the case, it becomes a bit more complicated, because then you have to use some special cosine or sine rules or whatever, and it just becomes a bit tedious. And you will find that even if you don't have two vectors, what if, let's say, we are adding 3 vectors or 4 vectors or 5 vectors, and you don't want to use this geometric approach for that, it will be a nightmare. So we have a much nicer method for solving these problems, and this is my favorite method to use. So the second method, so we have the same diagram here, and the second method we are going to use is the algebraic approach. Now don't be scared, this is much nicer and much more intuitive to understand, in my opinion. So what we need to do is we need to write the vectors with an I and j component. Okay, so just bear with me for a moment and I'll explain what these are. So I is the unit vector along the x dimension, and j is the unit vector along the y dimension. And what are unit vectors? Okay, so unit vectors have, by definition, a size of 1, and they're only used to indicate direction. Okay, they have a size of 1, so if you put a unit vector on, it does not change the size of whatever you're measuring, because they have a size of 1, and they're just used to indicate direction. They're extremely useful, and the best way to understand this, in my opinion, is just look at an example. So for R1, if we are going to describe the path of R1 to somebody, we can say, okay, so for R1 we moved 5 meters to the right and 5 meters up. Okay, and for R2 we moved 3 meters to the left and 3 meters up. Therefore, we can write R1 as 5i plus 5j. Alright, the 5i indicates that we have moved 5 meters to the right. The I follows the x dimension. So I is the unit vector along the x dimension. So 5i means we have moved 5 meters to the right. And 5j is the unit vector, j is the unit vector along y dimension. So 5j means that we have moved 5 meters up. And for R2 we can write it as minus 3i plus 3j. For R2 we have moved 3 meters to the left. That's why we have a minus 3i. And we have moved 3 meters up. So we have a plus 3j. So now, quite simply, and by the way, this is rectangular form. So the geometric approach, we write the vectors as a polar form, and in the algebraic approach, this is rectangular form. And we remember that R is R1 plus R2. So now it is very easy to add these two vectors together. So we have R as R1 plus R2. We just add the I components and the j components together. So we have 5 plus minus 3, or 5 minus 3 I, and we have 5 plus 3 j. So we can write this as 2i plus 8j. 5 minus 3 is 2, 5 plus 3 is 8. And so r is 2i plus 8j, and if we want to draw 2i plus 8j, it means we have moved 2 meters to the right and 8 meters up. And it makes sense, because let's look back at this. So for R1 we moved 5 meters to the right, and then for R2 we moved 3 meters to the left. So overall we've moved 2 meters to the right, which is 2i. And we also moved 5 meters up for R1 and 3 meters up for R2. So overall we moved 8 meters up. So we have plus 8j. That makes sense. So let's draw this vector out. So that means we moved 2 meters to the right and 8 meters up. And again, x is just the angle between the vector and the x-axis. So our resultant vector r is 2i plus 8j. Now let's check whether this agrees with our polar form, our geometric approach, and let's just check that. So the magnitude is 2 squared plus 8 squared square rooted, which comes out as 8.25 meters. So that's good. That is what we got in the for the geometric approach. And the angle it makes with the x-axis, x degrees here, is the inverse tan of 8 divided by 2, comes out as 76 degrees. So fantastic. It is exactly the same vector, and it completely agrees with our geometric approach, which is great. And I'm sure we can all appreciate that the algebraic approach is much nicer, especially when we have vectors without right angles between them and we have many vectors we want to add together. This approach is much more preferred. So now I have a few questions for you guys down in the comment section below. The first question is, write r, which is 10 with an angle 60 degrees with respect to the x-axis. Write this in rectangular form. Okay. The second question is, add the following two vectors together. So we have r1 equals 2i plus 10j, and we have r2 equals minus 5i minus 8j, and express them in polar form. So that means to add them together and express the resultant vector in polar form. Alright, thank you for watching. See you next time.